Hello, everyone. Welcome to another wonderful day of chemistry. So today we're going to be looking at ways we can control the rates of our chemical reaction. And to do this, one of the best ways to start is to go ahead and return to our look at Arrhenius. So let's go ahead and consider trying to slow down or increase the rate of a first order reaction of reactants going to products. So if it's first order, we have a linear dependence upon the reactant concentration, and again, a dependence upon the rate constant, which in and of itself is also going to depend on the Arrhenius constant, the activation energy, and the temperature. And so this gives us three easy controls of a reaction rate: concentration, activation, and temperature. So the easiest way to try and change a rate of reaction is to just increase the amount of reactants. If I have more reactants, I'm more likely to make product. And this is actually a fairly easy and convenient way to jumpstart a reaction. However, it turns out we're not always just made of reactants, so it's nice if there's other ways to speed up a reaction. And one of the other best options is what we were talking about last time: temperature. Because as the temperature gets higher and higher, more of my reactant molecules will have enough energy to get over that activation energy and make the product. And this happens by essentially increasing the rate constant as we have, again, a lower ratio of activation energy to temperature. Conversely, this means that if I cool a system down, that barrier gets effectively higher and higher, and any reaction can be brought to a halt. However, the exact temperature is required to essentially reduce any observable reaction will be dependent upon the activation energy of the system. However, it turns out we still have one last control, looking at the activation energy of a system. So this one gets a little bit trickier, as I have to find some way to change the activation energy of a reaction. And as we commented previously, when we're looking at activation energy, this is essentially the lowest energy pathway to go from reactants to products. So I have to change the pathway. And this is most commonly done by adding a catalyst to the system. And really how a catalyst works is by a catalyst binding to a reactants, it can often lower that highest energy step in the reaction. And so really, a catalyst is going to be any substance that increases the rate of the reaction, but doesn't actually appear in the net overall reaction. If it ends up being consumed, it's a reactant, not a catalyst. If it's produced, it's a product, not a catalyst. So one of the big tricks with how catalysts work is they change the reaction coordinate. They find some alternative way to go from reactants to products. And this is most commonly done via a general three-step procedure. My catalyst can bind to my reactants to make what's called a catalytic complex. This catalytic complex, there's something about the catalyst that makes it a little easier for this reaction to take place. After which, this product complex can then break apart, releasing my products and my catalyst. And so it really looks like we have catalyst as a reaction or a product here. But if we go through each step, we'll notice that every single step of the catalytic mechanism tends to have a cancellation. We end up producing our catalytic complex and consuming it. We produce our product complex and consume it. And even our catalyst itself, we take it up, but we also release it. And as a result, it doesn't show up in the net overall reaction. It's essentially just helping move from point A to point B. However, one of the big problems is that in order for a catalyst to actually speed up the reaction, it's required for each of these three steps to be lower in energy or faster than the direct formation. Otherwise, I'm not really getting any speed up. So let's go ahead and take this from generalities to a specific system. So it turns out formaldehyde can go ahead and decompose to make carbon monoxide and water. And this is often a good way to get rid of toxic formaldehyde. However, it's a little difficult for this hydrogen atom to move from over here to over here. So it's a little easier if we have a way to speed up the process. And one of the ways we can do this is by adding an acid as a catalyst. So in this case, that acid can be taken up by this oxygen to make a little bit of an unfavorable product. where I have this positively charged oxygen molecule. Now, it's worth noting that I wouldn't expect this to form at any great amounts, but one of the reasons why is that it is so unstable. So unstable, in fact, that you may notice I just made a water molecule. So this oxygen can go ahead and steal its electrons from that carbon and just head on out. And we've got released a water molecule and this kind of odd protonated carbonyl. But one of the tricks here is that carbon now has a positive charge. It is very unstable. So one of the ways we can stabilize this carbon is it can go ahead and steal its electrons back from the hydrogen and form carbon monoxide and releasing that free proton, which as long as you're in water is just fine. This is a very favorable step. And so let's go ahead and take a look at what this looks like from an energetic profile. So originally we have this very hard step of trying to take this hydrogen and move it all the way over into a very different location. However, from that point, it can immediately break apart. So again, simple, but difficult to do. The second part, a little bit messier. This protonation step is a little hard to make this to make this complex, which we're going to call an intermediate. However, this intermediate can break apart fairly readily, and once it does, can release the proton. So, well, none of these steps is exactly, these first two steps is exactly favorable. You'll note that they're not exactly as unfavorable as this giant, simple, but difficult Herculean effort. However, one of the problems is to effectively figure out how catalysts work, we have to try and figure out how we can couple the rates of individual steps together to make an overall process. So next time, we're going to be looking a little bit more at reaction mechanisms. Until then, take care.